I, Dr. S. Pethanachi Selvam, Head and Associate Professor, PG and Research Department of Mathematics. This session we are going to see small section countable sets in real analysis. What are the learning objectives of this course? Here we have to know the equivalent sets and what is meant by countable sets. And here what are the applications of analysis and what are the results in countable sets. And then we can see some more examples of countable sets. Real analysis is an area of mathematics that was developed to familiarize the study of numbers and functions and to investigate the important concepts such as limits and continuity. What are its applications? Real analysis serves as the basis for measure theory, axiomatic probability which follow to stochastic process. Stochastic process are used to finance trading, computer, network simulations, modeling, manufacturing and quality control, etc. Here the following symbols which are used to study the concept of countable sets and other topics in real analysis. Simply the real analysis concerned with the property of studying the real numbers, that is numbers in the real number system. Here the first property is that is concept in real analysis is countable sets. Here to study about the countable sets, we are in need of the following notations. It denotes the sets, the symbols of sets. Capital N denote the set of all natural numbers, that is it starts from 1 to etc. infinity. Capital Z denote the set of all integers, that is the set having 0, plus or minus 1, plus or minus 2, etc. up to plus or minus infinity. Q denote the set of all rational numbers. It will be of the form P by Q where Q not equal to 0. Here Q contains Z as well as N, and Q plus denote the set of all positive rational numbers. It does not contain the negative rational numbers, it contains only positive rational numbers. And R denote the set of all real numbers. R cross R denote the set of all ordered pair x comma y of real numbers. N cross N denote the set of all ordered pair x comma y of natural numbers. R power n, the set of all ordered n tuple of real numbers, and C denote the set of all complex numbers. C power n denote the set of all ordered n tuple of complex numbers. Here we are going to study the first concept of countable sets. Before defining countable sets, we have to define what is meant by a finite set and what is meant when do you say that two sets are to be equivalent. Here let us see the definition of a finite set. A set A is said to be finite if it is either empty or it has n elements for some n belongs to capital N. That is, we can label the elements of capital A by using the natural numbers 1, 2, etc. n for some n, and the number of elements of the set A is small n. If two sets A and B are finite sets having the same number of elements, then there exists a bijection from A to B, that is F is both on 1 and on 2. Two sets are finite sets are said to be the same elements, means they have the bijection, they should have the bijection mapping. Next one, when do you say that two sets are equivalent? Here for equivalent, two sets are equivalent, there exists a bijection from A to B. From these two sets, two finite sets have the same number of elements, means they have the same bijection map between A and B. Here from this equivalent, two finite sets are equivalent if and only if they have the same number of elements. That means already they have same number of elements means there is a bijection from A to B. That is a definition between equivalent sets. For example, let us see, take two sets 1, 2, 3, 4 and another set B as 1, 4, 9, 16. You notice the sets, the elements of the set B. Here the elements are the square of the elements of A. Therefore, we can define the mapping F between the sets A and B are defined by F of n equal to n square for all n belongs to the set capital A. Whenever you take 1, the image is 1 square, and 2, the image will be 4, for 3, the image will be 9, and for 4, the image will be 16. Clearly, every element in A have distinct images in the set B. Therefore, the map is 1, 1. If you take any other element in the set B, then there is an element x belongs to the set A satisfying the property f of x equal to y. So, we can for every y in y, there exists an element x in A such that f of x equal to y. Hence, there is a bijection between A and B. Therefore, the two finite sets A and B are equivalent. Now, always a finite set cannot be equivalent to its proper subset. How? We can see by example. Take a set, already we have taken A equal to 1, 2, 3, 4. You take a proper subset, name of A, named it as C. Take the proper subset of A, 1, 3, 4, that is named it as the set C. What is our result? A proper subset. There is no bijection between the set and its proper subset. Here you define a bijection between A and C. You note down that A containing 4 elements whereas C having 3 elements. From this we can't say that the map is not 1, 1 because the elements, each element in the domain A to be mapped onto the elements of C. But here the images are not sufficient. So, the set, the map 1, 1, the F is not 1, 1. So, that we can say that A cannot be equivalent to C. That means both finite sets cannot be equivalent to its proper subset. But you can take an infinite set, take any infinite set, but it can be equivalent to a proper subset of itself. Let us see by an example. Take an infinite set, the set of all natural numbers, you can say that set of all natural numbers A equal to n, and take a proper subset, it is also infinite, take the proper subset 2, 4, 6 etc. to n. That is the set of all even integers we are taking. Here clearly B is a proper subset of A, whereas A is an infinite set. Here you can define a map between A and B by f of n equal to 2n because the set B having only even number of elements 2n. So, 2n, that map is always a bijective map because 1 goes to 2 and the element 2 goes to 4 and 3 goes to 6 etc. So, every element of A having the distinct images in the codomain. Therefore, the map F is 1, 1. For every element in the codomain B, there exists an element x belongs to the set n satisfying the condition f of x equal to y. Therefore, the map F is a bijection. So, that infinite set be equivalent to its proper subset B. Hence, A and B are equivalent sets. Next one, after seeing finite set definition and equivalent sets, we can move to the definition what is meant by countable. Before entering the countable set definition, let us see the concept of when do you say that a set A is said to be countably infinite. Take a set A is countably infinite if A is equivalent to the set of all natural numbers. Equivalent definition says that there exists a bijection between A and the set of all natural numbers. Here you can say that by an example, that is take the example 1. Here the set A is the set of all natural numbers and your set B the set of all 2, 4, 6, etc. to n. So, B is equivalent to A. Why? Because between A and B there is a bijection. We have seen it in example 1. So, the set B is countably infinite. Whenever you take a set, it is said to be countably infinite means we have to prove that both A and n are equivalent. That is why we have proved the existence of bijection between the sets A and B. So, the set B is countably infinite. Now, let us see the definition of countable. We have seen all the finite set definition and what is meant by equivalent and what is meant by countably infinite. Now, see the definition, very easiest one. Set A, the set A may be finite or A may be countably infinite. We say that the set A is countable. So, A may be a finite set or A may be countably infinite. Countably infinite means there exists a bijection between the set of natural numbers. The set A is to be equivalent to the set of natural numbers. These are all the examples of countable sets. Here we have noted 3 or more 4 examples. We have seen through it. Z is countable. How can we prove that Z is countable? Here the proof says that it is an infinite set because it contains more than n elements. Therefore, the set is countably infinite. It is finite, not finite. So, it is countably infinite. If we prove that the set is countably infinite, by definition we say that Z is countable. By definition of countably infinite, we have to prove that there exists a bijection between Z and the set of all natural numbers. That is to prove that Z is equivalent to the set of all natural numbers. So, you define a function f between n and Z defined as n by 2 if n is even and 1 minus n by 2 n is odd. That means the elements 1 having the image, 1 is an odd number. So, f of 1 having the image to be equal to 1 minus 1 by 2, it is odd ns. So, your image 1 having the image as 0 and next one, what is that? 2, natural number 2, you put it, 2 is an even number. So, its image will be 2 by 2, therefore, the value equal to 1. So, 1 goes to 0 and 2 goes to 1, etc. It will map onto different distinct numbers from the set Z. Therefore, every natural number is mapped onto different elements of the set Z. Therefore, the map f is 1 1. Similarly, for every integer there exists a natural number satisfying the above property. Therefore, the map f is a bijection. It has an inverse image also. For every element in the codomain there exists an inverse image in the set n. Therefore, the map f is a bijection. Hence, we say that Z is equivalent to the set of all natural numbers. Therefore, by definition, we say that Z is countably infinite. So, by definition of countable sets, Z is countable. Next example, as it in the previous first example, here one set is given 1, 4, 9, then 16, etc. This set is a countable set. You take, let A equal to the set of all natural numbers and take our set B equal to 1, 4, 9, etc. We prove that the set P is countable. That means we have to prove that both N and B are equivalent sets. That means we have to find a map, define a map, and through the map we have to prove that the map is a bijection. If we prove it is a bijection, we say that both A and B are equivalent. Therefore, to prove that result, the map is defined as f of n. N is a natural number which is mapped onto the codomain element. You watch the codomain elements 1, 4, 9, etc. That means it is the square of natural numbers. Therefore, you define easily the map as f of n equal to n squared. Therefore, the every natural number 1 goes to 1, 2 goes to 4, 3 goes to 9, etc. Therefore, obviously, every element in the domain has image in the codomain set B. Therefore, the map f is 1 1. Similarly, we can prove for every element in the codomain 1 4 9 has a pre-image in A in the domain. Therefore, f is a bijection. Hence, the sets A and B are equivalent. That is, B is equivalent to the set of natural numbers. Hence, by definition, both this set is B set is countably infinite. That means by definition it is a countable set. B is a countable set. And then similarly we can prove, given the set N and A are equivalent. Instead of proving the set 101, 102, 103 etc. is countably infinite. Instead of proving this one, you can simply say that the natural numbers and the set A are equivalent. That means, as usual, you can define a map F between the natural numbers and the given set A. And it is defined as, you notice that in the previous example, the set B is only the square of natural number. Here note down the sets. The sets are 1, 2, 3 etc. in natural numbers, whereas in your codomain A having the elements 101, 102, that means 100 times bigger than the natural numbers. That is why I am defining the mapping as f of n goes to n plus 100. If the element is 1, you have chosen from the first domain, then what will be the image? N plus 100. That means 1 plus 100. Therefore, the image will be 101. If you choose the second natural number 2, your image will be n plus 100. That means 2 plus 100, 102. Therefore, you can get 1 goes to 101, 2 goes to 102, 3 goes to 103. Similarly, the image have all the elements in the natural number system will have different images in the codomain set A. As usual, you can note down the pre-image. Every element in 101 has a pre-image in n. Okay, it can be found by the relation f of x equal to y. That means n plus 100, that is the value, y plus 100 equal to your value y. Then finding the x value, that means y minus 100. Therefore, you can say that the value will become, you can get the images will be for 101, the image will be 1. For 102, the pre-image will be 2 and so on. Therefore, the map is clearly a bijective map. Therefore, the sets n and A are equivalent. In other way, we can say that a set A is countably infinite. Similarly, we can prove see some more results. That means some other properties of countable sets. Q is already we have seen set is countable. And what can you say about Q? After that Q is set, the next set is set of all rational numbers. Set of all integers is countable, we have seen it as a first example. Similarly, we can prove that Q is countable and Q plus is also countable. Also, we can be able to prove that n cross n, that means the set of all ordered pair of natural numbers. That means the set n cross n having the elements 1, 1, 1, 2, 2, 1, 2, 3 etc. That set of elements is also countable. Whereas, the set of all real numbers and complex numbers are not countable. Real numbers and C are not countable sets. That means they are uncountable sets. And also the other property, take any subset of a countable set. Already we have seen so many examples of countable set, and you can take a subset of a countable set. We can be easily, this is a statement of the property, but it can come from the easiest result. Here already we have proved Z is a countable set. You can take any subset, that means 1, 2, 3, it is a subset of Z, and we can say that you define a map between and n and 1, 2, 3. The set Z, that is you name the set as A. A is a subset of Z. A having the elements as 1, 2, 3. It is a subset of Z. Z is a countable set, and you take a subset and you define a map between them. Then what will happen? You can easily say that a subset of a countable set is countable. Similarly, you can prove that the Cartesian product of countable set. You take A and B are countable sets and take the Cartesian product denoted as A cross B, and the set of elements will be ordered pair. you take the countable set, Z is countable, suppose you take two countable sets, that means you take the first set A equal to Z and second set Z, another set as Q, both Z and Q are countable, then what can you say about that Z cross Q? That product of countable set, Cartesian product, contains the set of all ordered pair of elements from A cross B. Therefore, the Cartesian product of countable set is countable. This is similar to n cross n. N cross n means that is also the Cartesian product of countable sets. So, n is a set of natural numbers, n is a set of natural numbers. That product is called as a Cartesian product. There we have same sets are there, n cross n, r cross r, like that. But here Cartesian product of any two countable sets, it also be countable. These are the properties of countable sets. Thank you all. Let us see in the next meet. Thank you.